Namaste everyone. Welcome to Wave Optics class. So we have seen Huygens wave theory in the previous class. Corpuscular theory failed because it said that light travels faster in denser medium and bends away from the normal when the ray travels from rarer to denser. But actually when the ray travels from rarer to denser, it bends towards the normal, its speed decreases. But according to corpuscular theory, it increases. When it travels from rarer to denser, velocity increases, which is wrong. Practically it is wrong. Practical observed fact is velocity decreases as the light travels from rarer to denser medium. So it failed. So later on Huygens said that light is a wave and it is not a set of particles, it is a longitudinal wave, but he corrected that light shows polarization, that's why it is a transverse wave. But he failed to say how does light travel in vacuum. But later on it was corrected by electromagnetic wave theory, that is given by James Clerk Maxwell. So Huygens gave his own idea that there are, suppose it is a point source of light, there are spherical wavefronts which are growing in size and becoming larger and larger. Every point on the this primary wavefront acts like a secondary source and it gives its own waves and the wavefront grows. And all these secondary waves move in only forward direction, so the light moves in the forward direction. So a point source emits a spherical wavefront, we have seen that. A linear source emits cylindrical wavefronts, and any source, maybe point source or linear source, at very large distance emit, we receive plane wavefronts. When it is received at from a large distance, we receive plane wavefronts. So what type of rays that we receive from sun are parallel rays, and it is equivalent to plane wavefront. Okay. Now using Huygens theory of secondary waves, let us try to get try to explain how does light travel, or how does the light bend in prism, lens, mirror, and as well as try to obtain Snell's law. That is what is our aim today. Now Huygens gave a very beautiful explanation regarding this. Now suppose this is a refraction surface which can bend the light in a particular direction. Now according to Huygens, he didn't make the same mistake as made by Newton. He said light travels slower in denser medium, faster in rarer medium. That was corrected in Huygens theory. Now suppose a parallel beam of light is incident on a surface, say like this. A parallel beam of light is incident on a refracting surface. Now what will happen as soon as it enters into the denser medium, say. So this is a parallel beam. Let me make it still parallel because I will have to show many rays here. Yes. So like this. Now a parallel beam of light contains many wavefronts. When they fall on this surface, secondary wavefronts will start traveling, and they travel in different directions. Okay. And suppose this is the normal drawn here, and this is the angle of incidence, right? So if you take this as a single ray, then this is the angle of incidence. So I will write the arrow mark here. And light is filled with this gap, parallel beam. This is not a single ray, it is a parallel beam of light. And okay. Now suppose you divide it into a number of rays. A ray here, like this. Number of rays like this. Now since the ray is incident, the beam is incident at some angle I, the left edge of the beam is incident on this surface, or it starts its journey to the surface in the beginning itself, whereas the rightmost ray in the beam reaches this surface at the end. So by the time this surface starts its journey inside this medium, this ray would have been somewhere here. So I will drop a perpendicular from here to this one, and I will say here. So it is like people going in a march fast, right? Suppose this is a set of soldiers and they are showing a march fast here. So as they come like this, by the time this leftmost soldier is here, the rightmost soldier will be here. Where will be the other soldiers? The soldier who is moving in this path will be somewhere here, soldier moving here will be somewhere here, and this person will be here. So the different rays of light in this beam, if you could take a beam as a collection of rays, different rays of light in the beam will be in different positions. Now for the first, in the beginning, this soldier gets a chance of entering into the medium, and this soldier is still traveling in the first medium. Let V1 be the velocity of light in the first medium and V2 be the velocity of light in the second medium. So as suppose this is a denser medium, suppose this is glass, definitely the speed of this soldier will start decreasing and he will bend to some other angle. And this soldier is still traveling in air, so he will maintain his own speed, and this soldier is still traveling in air like this. So they will continue their journey. Now, by the time this soldier reaches here, this wave might have already entered into glass and it might have started its journey. This might have entered glass, this might have entered glass, this might have moved forward. So, what is the distance traveled by this wave which hits this surface initially by the time this wave reaches here? It will travel certain distance. Will it be this distance? This distance remaining for this wave. So how can you write it? So we know the formula. Velocity is equal to displacement by time, delta x by delta t. If I write it, now if I take the velocity of the light in the first medium as v1, then v1 is equal to, displacement is this one. I will name this a, b, c. Displacement is bc divided by, and time taken is say tau. We will take it as a common time. The time taken from by the wave from at the rightmost end to reach from B to C, that is the time in which this has started its journey inside. BC by tau, and what is BC? BC is equal to V1 into tau, right? So shall I write this distance as V1 into tau? V into time is the displacement or distance. So this wave traveling with the speed v1 will take to travel this distance will take a time of tau, and that distance is v1 into tau. That means in a time of tau, say time taken by the wave to travel from here to here is tau. Then how much is this distance? V into tau, because velocity is displacement by time, displacement is velocity into time. So this wave will travel a distance of v1 tau in a time of tau. By that time, what this will do? Will it proceed like this at the same distance here? Not possible, because the medium through which this wave, which is the secondary wave in the leftmost end, the medium through which it will travel is a different medium compared to this one. So still in time tau, this is moving in air, whereas this is not moving in air, it is moving in some other media where the velocity is less. So definitely this will not travel this much of distance, it will travel a little bit less. But will it continue its journey in the same direction? Suppose it is little bit less. How much less? How much less means how much distance it will travel in the same time tau, because whether the wave is traveling in air or whether it is traveling in glass or water, its time is same. Time cannot be different. In a time of tau, say 10 seconds, this reaches here. In the same 10 seconds, this will move forward inside the medium. But where it will move forward? Will it move forward here? Will it move forward here? It will move forward here. Will it move forward here? Don't know. We know that it changes the direction by the time it enters into the other medium. And you know that this distance will be more, and whatever the distance this will travel in that 10 seconds, what I have taken for tau will be less. This distance will be lesser than this, because here the speed is less. So what is the distance traveled by the wave here inside the medium? I don't know. Sorry, distance is v2 into tau, because velocity into time gives the displacement or distance. This will travel a distance of v2 tau, and definitely v2 tau is lesser than v1 tau, because v1 is greater and light travels slower here. So this length should be more, this length should be less. But the question is whether this length is here to here or here to here or here to here or here to here or here to here. Don't know. So in order to find it out, for the time being, let us not bother about the direction where this wave or this soldier will move. Whether this soldier moves in this direction with the distance which is lesser than this, whether he moves in this direction to a distance which is lesser than this, whether he moves to this or this, don't know. So in order to find it out, we will do one thing. We will draw a circle of radius v2 tau. We know that distance is v2 tau, right? v2 into 10 seconds. Distance is lesser than this, but in what direction? Don't know, right? So with this as a radius, draw a semicircle. Did you get that now? That means the point where this wave will reach inside the medium, which is lesser than this, maybe here, maybe here, maybe here, maybe here, maybe here, anywhere, we don't know. Okay, so the wave which enters into the medium where its velocity is less, the wave which enters into the medium where the velocity is lesser than that in the first medium may be anywhere here if you connect it like this. Don't know where it is. What about this one? See, this wave was here, and this will reach here after some time, right? It will continue the journey and it will reach here after some time. That means this will start its journey inside this medium little bit later than this has started. So where this wave will be? This wave will not get a chance of traveling for 10 seconds inside this medium. It may get some 8 seconds or 5 seconds or 7 seconds. So what about this one? This will take still less time to travel inside the medium because it has hit this surface even later than this one. So it may take some 4 seconds, or it may get a chance of traveling for 4 seconds. This may get a chance of traveling for 3 seconds or 2 seconds, and this may not get any chance of going into this medium. Why? Because when this hits here, this will be here, and after 10 seconds this will reach here. After 10 seconds this will go and it will move here and go little bit inside. After 10 seconds it will move here and it will move little bit more inside. This will move here and it will travel little bit more. This is the highest traveled wave, secondary wave inside the medium. Okay, so how much distance this will travel then? It will travel a distance which is equal to V2 into, say this is V2 into 10 seconds. This will travel a distance of V2 into 8 seconds. What about this one? V2 into, say, some 5 seconds. What about this one? V2 into some 2 seconds. So the distance through which these three waves will travel will be lesser and lesser. So where it will be then? Whether it will be here, here or here. If you have any confusion, draw a circle with that as center. Yeah, this wave as center, draw a circle. With this as center, draw a circle. With this as center, draw a circle. With this as center, no circle can be drawn because, sorry, it is not a line. So with this center, you draw a circle. With this center, no circle can be drawn because this wave will just reach here by 10 seconds. 10 seconds earlier, this was here. 10 seconds earlier this was here, but inside it might have moved a little bit forward because it may have some even it will get a chance of 2 seconds to travel inside. This may get a chance of 5 seconds, so on. Now this has just reached here. Now if you want to write this wavefront, parallel wavefront, plane wavefront, parallel rays. You know that when a ray of light is incident on a glass slab, its direction changes, but parallelism is not lost. It will be still parallel ray of light. So if you take a parallel beam of light incident on glass, still it is parallel, no doubt. And if it has to be parallel, where should be that ray of light? And you should get common points which will join all these things. Common points which will join all these curves is a tangent to the curve like this. Of course I have to little bit increase the like this. So you connect all the tangents to these curves. What do you mean by this? The wave which is entering here must have reached here. The wave which is entering little bit late, this will take 10 seconds to enter into. This will take only, it will get a chance of traveling only for 8 seconds. This may be 2 seconds. This will just hit here, and all of them will have a common line here. So this is the common one, and the wave will continue to be like this. And once after 10 seconds this enters here, it continues like this. Hope you have followed this explanation. I will explain it again here. So what you have to do is, if you want to get the refracted wave, what you have to do here is, let us assume that this is 10 seconds. Of course, this need not be given. This is only for understanding. This tau is 10 seconds. So this is 10 seconds back. This has just hit the surface. In 10 seconds, it may be anywhere here, right? It may be here, 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 or here. But this distance is always less than this because this travels in a rarer medium and it will travel more distance in 10 seconds, and this has entered denser medium, it will travel lesser distance. What about this wave? This wave will be somewhere here, anywhere. This wave will be somewhere here, this will be somewhere here, and this will be just hitting. Now if you want to know where are the waves, whether this one is here or here, you have to connect all these one by drawing a tangent. So this will be coming here, this will be coming here, and this will be coming here, and this will be coming like this. And now this is normal to all these rays. This is a plane wavefront again. So plane nature is not lost. Now if I continue the angle of refraction, this one, normal. This is the angle of refraction. That is how we say it. And you need not draw all the circles. I have explained it that how to find out the refracted ray. So this is the plane wavefront. I will draw it, redraw it. So because here it is not a very big derivation, very small derivation. Only the thing is you must understand what you are doing. This is a very new concept, very new idea. So I will take a parallel beam of light and I will make it to fall on the refracting surface. According to Huygens theory, every point of the primary wavefront is a collection of secondary sources. So when it falls on this surface, secondary sources will start moving out, right? They start their journey. So when they start their journey, okay, but who will get the first chance of starting journey in the other medium? That is nothing but this wave, this one. That will get a first chance. By that time, what this extreme wave will be doing? It will be, you draw a normal, this is a perpendicular line, and it will be here. I'll name this A, B, and C. Now you draw a normal here. Then this is the angle of incidence. And if you want to know where is the wave here, by the time this reaches here, and this will travel a distance of V1 tau, because the V1 is the speed of light in the first medium, and this is V1 tau, this distance, and this is C, and this will travel a lesser distance, V2 tau. So just an arc is enough. You need not draw the full circle here, just an arc is enough. And for this arc, what you have to do is you have to draw a tangent like this, normal. And where will be the refracted ray then? It will be here, and this will be the angle of refraction, and okay, this, and draw a line parallel to this like this. So this will be lagging behind by 10 seconds or so. And what is this one? This distance is the distance travel. Okay, I will avoid, yeah, I'll name this as A here. This is V2 tau. In the same 10 seconds of this traveling, how much this has traveled? Lesser than this one. So light ray bends towards the normal. Okay, right. Now we have to prove Snell's law, and all these things are supportive data, so I need not draw that. Now I can rub this. So this is V1 tau, more distance because it is rarer. This is denser, lesser. So the time is same. In 10 seconds this has covered this much. In the same 10 seconds this has covered less. But of course, after once it enters here, this will also have its velocity lesser. Now I want to, and this is R. Now I want to transfer I and R to this triangle and this triangle. What I can do? And this is a normal drawn. In order to show that this is a plane wavefront, in order to show that this is plane, I have drawn a normal. And if this is 90, if this is 90, this is I, this is 90 minus I, correct? That is 90 minus I. But this is 90. And if this has to be 90, this should be I. Because you see, I plus 90 minus I, 90, we get it. So I will rub this. This is I. This is I, this is 90 minus I, because this is perpendicular like this. And if this is 90 minus I, this is perpendicular, this should be I. So I'll rub this also. I will avoid too many letters there. Okay, now R you have to transfer. Where we will transfer R? R has to be transferred. This is R, but this is 90 degrees. So this is 90 minus R. If this is 90 minus R, this is 90. Total three angles should be 180, so this is R. Now add it, 90 plus 90 minus R. So that is, okay. 90 plus 90 minus R plus R. So that gives you 180, right? So this is R, but this is perpendicular 90 minus R, but this is already 90. Total should be 180, so this should be R. You just count it, you can get it. Okay. Okay, that is R and this is I. Now how to prove Snell's law? Very easy. Let this be a medium of refractive index N1 and this be a medium of refractive index N2. velocity of light here is v2, velocity of light here is v1. This is rarer and this is denser, so v1 is taken greater than v2. Now, you take the triangles. I'll take the triangle ABC. What I can get it from here, this is 90 degree because this is the parallel wavefront showing a line. This is also another one line. Okay, what is sin I? Sin I is equal to this I, opposite side BC by hypotenuse. Hypotenuse is AC. Equation 1. Take sin R in this triangle. Sin R is equal to opposite side, I will take this as AD. Okay, AD divided by hypotenuse. Hypotenuse, this is 90 because this is the line which shows that it's a plane wavefront. Hypotenuse is this one, AC. Of course, BC and AC I could have substituted as V1 tau and V2 tau. I can do it later. Now divide them, sin I by sin R, because that is what gives Snell's law. Sin I by sin R, sin I by sin R equal to, what is sin I? BC by AC. So shall I, okay, BC by AC into sin R is AC by AD. AC by AD. So this gets cancelled. What is sin I by sin R? Sin I by sin R is equal to, BC is V1 tau and AC is V2 tau. You can see it here. BC is V1 tau by V2 tau. Tau gets cancelled. That's why I have taken it as some 10 seconds randomly, because it has nothing to do with the derivation finally. In 10 seconds this will travel here. In the same 10 seconds it has started its journey inside. So what is V1 by V2? Sin I by sin R. So sin I by sin R is equal to V1 by V2. This is 1. Now, we take sin I by sin R is equal to N2 by N1, right? N2 1 is equal to sin I by sin R. So from where we will get it, sir? Now suppose this N1 is the refractive index of this medium only. Say first medium is water and this medium is glass. If N1 is the refractive index of this medium with respect to air, when this water is taken in air, that is the absolute refractive index. Now how to write this one? It is the velocity of light in air divided by velocity of light in the medium. When this glass is taken separately in air, N2 is its refractive index. So what is N2 now? N2 is velocity of light in the first medium, air, divided by velocity of light in the second medium. So can I get these two values in that formula? What I can do is multiply and divide by C. So if I multiply and divide it by C into C by C, I will write C by V2 as it is, C by V2. This one I will take it as it is, and V1 I will bring it outside, denominator. 1 by C by V1, is it okay? V1 comes to the numerator, V1C, yes, V2C, yes. Now what is C by V2? C by V2 is N2. It is the velocity of light in air divided by velocity of light in the second medium. Suppose the first medium is air, then it is the refractive index of the second medium with respect to air. What is C by V1? It is the velocity of light in air divided by velocity of light in the first medium. That is the refractive index of the first medium with respect to air. So shall I write it as N1? So what is sin I by sin R? Now you get the perfect Snell's law. Sin I by sin R is equal to N2 by N1. Even this is also not bad. This is also okay. V1 by V2. So sin I by sin R is equal to V1 by V2. This is also good. So this is how we get Snell's law from refraction using Huygens secondary waves. So he has a beautiful idea of waves, secondary waves traveling different distances inside the medium. Now how do you draw the same diagram when the light travels from denser to rarer medium? That we will see. So shall I rub this one now? Same, only diagram is enough, derivation is going same way. So when a wave travels from, when a light travels from denser to rarer medium, say, let a plane wavefront be incident on glass, let it be traveling through air. So N1, N2 and N1 lesser than N2, sorry, greater than N2, denser to rarer. Let a parallel beam of light be incident. Now we will check different wave fronts when they hit the surface. Where are they now? What is their position? When the secondary wave starts moving inside this medium, by that time this wave will be lagging behind because it is incident at some angle. So all the soldiers are moving in a march fast, and they are together like this here. This soldier is parallel to this soldier, and this soldier is parallel to this soldier. They keep on moving. By the time this soldier starts entering into another medium, say sand or concrete or whatever it is, this soldier is here, correct? Now suppose this is AB. Now draw a normal angle of incidence. Now what happens to them? As soon as this soldier starts his journey inside, that is secondary wave from here is starting his journey inside. Now what happens? This is still in the first medium and it is continuing its journey. Let tau be the time taken to move from here to here. So what is this distance? V1 tau. But this has started its journey inside, which is a rarer medium, and it can travel with a speed greater than that in here. Suppose V1 is the speed here, V2 is the speed here, V2 is greater than V1, V2 is rarer. Glass to air, water, for example, this is rarer. So here this can travel larger distance, and you have to take this length and draw an arc here to trace this ray. So you have to take a larger one. Am I right? You have to take a larger circle, because I don't know where this wave might be. This is center and a larger circle like this. This wave may be here, maybe here, maybe here, maybe all these distances are same. And if you want to know where the wave is, you have to draw a tangent to this circular path. You need not draw the full circle. You can draw it just an arc, and you have to draw a tangent somewhere here, and you have to find that this moves like this, and similarly this one. Only tangent will touch it here only. So this is the angle of refraction, and it bends away from the normal, and remaining things will be same. So this length, that is V2 tau, will be greater than this length V1 tau. Reason is this, in a time of 10 seconds, say, this gets a chance of traveling lesser distance since its speed is lesser here, and because it's a denser medium and this is a rarer medium. As soon as this enters rarer medium, it gets a chance of traveling faster, so it can travel a larger distance, and such a larger distance can be covered with this circle, but we don't know whether it moves here or here or here or here or here. Don't know whether it has moved like this and reached here, same distance V2 tau, same distance. In order to find it out, from here you draw a tangent here, then you will find that it is traveling here. Now suppose if you imagine this wave, of course it has reached here little bit later, but still it will get a chance of traveling inside by the time this reaches here, but not as much as this much. So it will travel little smaller distance compared to this length. So if you draw a curve for this one, it will be like like this, and that curve touches it here. Similarly for this wave, there will be a curve like this, and that curve touches here. So all the common lines are here. This is the refracted wave. It bends away from the normal. Angle of refraction is more. So very nice explanation for refraction, right? The ray of light traveling and moving away from the normal when it travels from denser to rarer, rarer to denser, bending towards the normal. Okay, now, so that is one explanation, right? This is Huygens wave theory. And using this theory, Huygens was able to explain the reflection also. How does light undergo reflection, and why is the angle of incidence equal to angle of reflection? Because you know, in reflection I equal to R, angle of incidence equal to angle of reflection. So in order to analyze this, we can take it like this. You take a reflecting surface, say mirror, plane mirror. You know that you have to prove now angle of incidence equal to angle of reflection using Huygens theory. Now let a beam of light be incident on this surface. You know that it undergoes reflection. It is incident like this. So this is it's a beam of light, collection of rays. Now what happens is, imagine that it is a set of balls like this. Balls here. All the balls are thrown like this. Now which ball hits the surface first? This one. By the time this ball reaches here, this ball will be somewhere here. Draw a normal, perpendicular. Correct? By the time this ball reaches here, so let us imagine that they are thrown with their machine with a very great velocity. They don't follow the parabolic path. They are thrown it like with a very high speed. So this hits. By the time this ball will be somewhere here, and this hits the surface and starts its journey in the reflected direction. So let this be the reflected path. And you know that angle of incidence and angle of refraction are same, but we don't prove it now. So I will take that this is the angle of incidence and angle of reflection. I don't know whether I and R are same or not now, because I have to use Huygens theory and I have to prove that I and R are same. Okay, this is the reflected beam. Of course, it doesn't change the color, just I change color for your understanding. Now, how much distance this wave after reflection will travel by the time this ball reaches here, right? This ball starts reflecting process earlier, because it touches this surface first. By that time this ball is here. Where is this ball? This one will be here. Where is this one? It will be somewhere here. These balls are yet to come now. They were traveling like this and they are yet to hit the surface. This has hit the surface now. This is here, so it starts reflecting journey. Now by the time this reaches here, and let V be the speed of light in that medium. Of course medium is not changed, you need not worry about this, because it is a reflecting surface, no chance of light going into, so V is enough. Now suppose it takes 10 seconds to reach from here to here. What is this distance? That distance is V tau. Velocity into time gives the displacement. So velocity equal to displacement by time. Displacement is velocity into time, so it needs, or it will travel V tau distance. I will write this as BC. So that wave, secondary wave which was here, has traveled BC in a time of tau. What this will do? This, when it is here, this has traveled, this has started its reflected journey. This will come here and this will start here. So both were here. Now this will come here and it will start reflected journey. Now what is the reflected journey distance? Definitely it is same as V tau. Why? Because this is moving back to the same medium. So how much this has traveled from here to here, distance wise, this will travel the same distance from here to here. Am I right? So I will cut this with the same distance V tau here, and I will name it as some D or so. I don't know what you have used in book. So this has started, it will reach here. Okay, and I don't know where does it reach actually. I have to draw a circle here, whatever it is. What about this ball? By the time it is somewhere here, this ball will hit, and this ball will hit, and it will start its journey like this, and it will reach here. What about this ball? This goes here and reaches somewhere here. So all these wave fronts, and what about this one? This will be somewhere here. So all the wave fronts will be seen, and if this is hitting and coming here, if this is hitting and coming here, and different points like this, and if you join them, it will be here, right? The reflected wave will be here. Did you get that? This wave reflected and went here. This wave reflected and went here. This wave and reflected went here. Just imagine that we are throwing the balls. So when the ball was thrown and here and hits and moves up to this ball will follow it and it will move up to this, because it is lagging behind a little bit, and this ball will hit and it will reach up to this. What about this ball? It has just hit, it has not started its journey, and so all the balls will hit to the surface and they will return back, and this is the reflected wave. Hope you can follow this. Now, so because this will start the journey a little bit later, suppose you count it for 10 more seconds, this will move forward and this will come here. So the parallelism is maintained. So if you incident a parallel beam of light on a reflecting surface, reflected ray is also a parallel beam. Both are parallel. Now we have to prove that angle of incidence equal to angle of reflection. So I will redraw it. Reflecting surface, this is a plane wave front incident on the reflecting surface, and by the time this is here, the other wave is here. So what about, so this is only a line which is shown to see where its companion is here, right? Where the companion of this soldier, friend of this soldier, when this soldier is here, his friend is here. When he is here, friend is here. When he is here, friend is here. And this soldier starts his reflected journey like this. And when this one reaches here, this soldier reaches here, say. Okay, then where are the other soldiers, reflected soldiers like this? They will be, all will be found in this line. So I will use different colors. Yes, this like this. Now name them A, B, C, okay, D, like this. Now draw a perpendicular here. This is I. I'll take this as R. Now transfer this I and R. You know that this line and this line are perpendicular, correct? Now what else I can do? If this is I, this is perpendicular, this is 90 minus I, but this is 90, so this is I. Do you agree? If I can change the colors, this one normal and this one, if I can change these two colors, see this I will change this to white. Okay, this white and this yellow and yellow, they are perpendicular lines. So if white and white perpendicular set is turned by an angle I, suppose if I push this by an angle I to the yellow line, when this comes to this yellow line, this comes to this yellow line, this covers an angle I, this covers an angle I. That's also one of the proof. Or this I and this one are perpendicular, so this I and this is 90 minus I, but this and this are perpendicular. When this is 90, this should be I. Okay, that I is transferred. What about R? We have to prove that I equal to R. This is the angle of reflection. If this is R, then you see this triangle. If this is R, what I can prove now? This angle is 90 minus R, correct? This is 90 minus R. What about this one? 90, because this is the normal drawn to this one to show how is the reflected beam of light like this. So this is a normal, as if you have a line here. This is for the reflected wave. So this is 90, this is R, this is 90 minus R, 90 minus R and 90. So this is R. Hope you have followed it, right? Okay, I'll rub this. So this is a plane wavefront showing line, and this is plane wavefront showing line. This is also showing plane wavefront. Okay, now, so this is R and this is 90 minus R. This is 90 minus R, and if this is 90 minus R, this is 90, then this is R. In this yellow, blue and pink color triangle, yellow, blue and pink color triangle, this is 90, R, 90 minus R, 90, R. So this is I. Now you just take sin I and sin R, you will get this back. What is sin I? And you know that after reflection, this AD is V tau, right? AD is V tau. Why V tau? Velocity equal to displacement by time, and displacement is velocity into time. So in a time of say 10 seconds, this reaches here. So BC is also V tau. In a time of tau, BC reaches here. In the same time, this reaches here. So AD is also V tau. Velocity is same. So it falls like this. So here and here. By the time this reaches here, this will continue the journey. Now, okay, sin I. Sin I is opposite side BC by hypotenuse. This is angle 90. Hypotenuse is AC. What is sin R? Sin R is equal to opposite side AD, right? AD divided by hypotenuse AC. But this can be written as BC is V tau, and what is AC? Okay, AC. What is AD? AD is also V tau. By the time this reaches here, this will reach here in the same medium. So AD is also V tau. So what do you mean by this? Right hand side of these two equations, that is sin I and sin R are same. Sin I is equal to sin R, I is equal to R. If sin theta is something it is called sin theta dash, then theta and theta dash must be same. So I and R are same. So angle of incidence equal to angle of reflection. That means light gets reflected back in the same angle with respect to the normal. So this is how do we prove for reflection. Okay. Now Huygens wave theory is also used to show the refraction in the case of lenses and mirrors. Now suppose you take a lens. We know that in terms of beam of light or rays of light, how do we show? If you show parallel beam of light on an incident on a convex lens, convex lens is a converging lens when it is kept in air, and it converges all the rays of light. And you know that any point source of light emits diverging rays, right? Point source of light emits diverging rays. So what is the wavefront emitted by it? It is a spherical wavefront. And suppose it is a reverse case, suppose we have converging rays of light. It is also a spherical wavefront, but it is a decreasing sized sphere. If it is a diverging ray of light, it is an increasing sized sphere. If it is a converging beam of light, it is a decreasing sized sphere. Spherical wavefronts, the size will be decreasing if it is converging beam of light. If it is diverging beam of light, spherical wavefront size is increasing. Now, how can you say that this lens is converging the rays of light? Very simple. Take a plane wavefront. What do you mean by plane wavefront? You show it in planes like this, right? When a plane wavefront hits the lens, a convex lens, say. Now what happens is, it is very similar to parallel rays. In terms of rays, it is parallel. In terms of wavefront, it is plane. If a parallel beam of light is incident, now some wavefronts hit the glass lens, say, in the beginning, right? It hits it here. And the wavefronts which are moving here, they will take little late time to hit here. And the distance to be traveled inside the lens for different wavefronts, secondary wavefronts I am talking about, are different. The wavefront which is entering here has to travel more distance, whereas the wavefront which is traveling here has to travel lesser distance. And here little more, here highest, again less. So what happens is, all these were traveling together, all the soldiers were moving parallel to each other. This extreme soldier looks into this soldier, he is very parallel to him, and this extreme soldier looks into this soldier, parallel to him. So the two friends are parallel and parallel as they move. But here is a sand ground. But sand is not put in a parallel way, or it is not parallel to the motion. The sand bed is like this, imagine. And this soldier has to travel more in sand, this soldier has to travel less in sand, this soldier less, this one little bit more, this is highest. So what happens? By the time they come out, how will be the soldiers now? How will they look like if they look at their friends like this when they go on a march fast? This soldier will be moving little bit forward because he has to travel little bit less in sand. What about this soldier? This soldier has to travel little bit more in the sand, so he will lag behind, because you know that in the sand speed is less, in the lens velocity of light is less, so this will lag behind little bit, whereas this will travel more. What about this one? This has to travel little average distance inside the sand. It will be moving little bit forward, but not as much as this one, because this has to travel very less in sand. This person has to travel little more in sand compared to this, so he will lag behind little bit than this person. So if you connect all these waves which are in same phase, so you will get a spherical wavefront. And if you move forward, what happens is, this person will travel here, this person will travel here, and the wavefront keeps on decreasing its size, and at one point it will converge, and that is what you call parallel rays converged by a lens like this. So wavefronts entering into the lens, because of its shape, have to travel different distances inside the lens. So, and the wave which is hitting the middle part of the lens have to travel more distance, and the sides will be less distance. So what happens is, by the time they come out, they will have a different shape but same phase. So they will form a spherical wavefront, and that spherical wavefront keeps on decreasing in its size, because they will change the direction also. As soon as they enter the lens, their direction will also change like this, because of the change in the speed, you know, that is refraction. So that makes the converging beam. Okay, what about a mirror? We will take a mirror now. Okay, you can take a lens, prism also. The same thing happens in a prism. Suppose you take a prism, incident a parallel beam of light like this. The soldiers will go on march fast. Now this one says, I have met that sand bed. This says, no, I have not met the sand bed, and I have not traveled in the sand bed yet. It is at a certain distance, and this person starts his journey. He has to travel more in sand bed, whereas this one has to travel very less, average distance. So what happens? All of them will turn. So this will be lagging behind too much. This person may be traveling too much, average distance, and this person has like this. So they will be in this condition. If this person looks at this person, he will be here, and he will be surprised to see that this has traveled a little bit more. Why? Because this person has to travel, or this secondary wave has to travel lesser in prism, and that makes that secondary wave to travel more. So finally, of course, it will change the direction also. Finally, the wave will bend like this. And you know that if parallel beam of light is incident on a prism, it bends towards the base. Of course, because as it travels through this, the angle will also bend, because the velocity will change. So secondary waves will have again plane. This is a plane wavefront. This is also a plane wavefront. The plane characteristic is not lost. The parallel beam is not lost, but only the thing is it has bent. Now what about a mirror? Concave mirror I'll take a concave mirror, and in a concave mirror, you know, when parallel rays are incident on a concave mirror like this, they get focused at the focus, right? Parallel rays always get focused at the focus. Now if parallel rays are, if a plane wavefront is incident on a concave mirror, what happens? They hit the concave mirror surface. But when they hit the concave mirror surface, this one hits first, so it gets reflected. What about this one? After reflection, this wave, suppose it reaches here, this wave, after a little late, it will hit and it will be here. What about this one? It will hit this mirror not as early as this one, but little late, and it will be somewhere here. Okay? And this one is hitting and returning back. Let us assume that this has just hit. And what about this one? This has hit like this and it has returned back. This has hit earlier and it has returned back more. So if you connect all these things, you will get this one, reflected beam, right? This will hit this earlier and return back this much. But by that time, this will just reach here. It won't return back at all. And what about this one? This will hit and return back little less, not as much as this one. The reason is this has to reach the mirror a little bit late. So what happens to the reflected wavefront? If you collect all these waves which are in phase, you will get a sphere, and its the size, because you know that they form converging beam. So the size of this wave keeps on decreasing and the ray comes to the focus. So if the plane wavefront is incident on the concave mirror, reflected wavefront is a spherical wavefront, and it is a converging beam of light, and it gets focused at the focus. And this is the way in which we have explained all the wave theory in terms of wavefront, not in terms of parallel beam or so. So if it is a plane wavefront, it is a parallel beam of light. If it is a spherical wavefront of increasing size, diverging. If it is a spherical wavefront of decreasing size, converging. So a new world or new idea of explanation of Huygens. So very beautiful explanation, and using this theory he was able to explain many things like interference, diffraction, reflection, refraction, even polarization he was able to explain. So all these things were explained by Huygens theory. So this may be asked for the examination. How? Explain or obtain Snell's law using Huygens theory. What are the main points of the Huygens theory, features of the Huygens theory? That every point on the wavefront will act like a secondary source, and every source of light emits wavefronts, and the secondary envelope of these secondary waves gives the next wavefront, and the wavefront grows, and all these things. I have told it, and you have to prepare it for the exam also. And show that using Huygens theory, the incident and the reflected rays form the same angle. That means angle of incidence equal to angle of reflection. Or you may be asked to draw the diagram of a concave mirror forming the converging spherical wavefronts after the plane wavefront is hit on it, and what happens to the plane wavefront hit on a prism, or when it is hit on a lens. All these diagrams, very simple explanations. So study all these things. A little bit theory is more needed here, and with all these ideas we will go to the next one, that is interference chapter. And here also you need lot of imagination, and all the things what you have studied in waves, the phase and superposition, everything. But we will recap all the things which you have studied in first year, then we will move on to the theory. And till then, keep studying this one. Don't waste your time, because the class opening is going away and away. Don't know when it will open, but once it opens, you will never get time for digesting anything. So everything will keep on running. So if you study now, I think it is better. better you will have the things with you, and you can save a little bit of time, or you can relax once the classes start. Otherwise it will be like a hectic schedule. So keep studying all these things. Hope you will do well. So thanks for watching this video. Keep doing well. Thank you. Namaste.